The published role view of a logic IDM plus foundry business should be read as evidence of breadth, not as a claim that every mission has equal hiring volume. Public materials commonly show roles in design, process technology, manufacturing, packaging, product, software, and customer enablement. What matters is the technical relationship among them. A designer may work several organizational layers away from a process engineer, yet the success of the product depends on their outputs being compatible. This is also a useful reminder that career mobility can occur through interfaces. Expertise in validation, product engineering, or design enablement can connect multiple parts of the organization. A pure-play foundry makes manufacturing technology and manufacturing execution the core product offered to external chip designers. Process integration, unit processes, equipment, metrology, inspection, process control, yield, manufacturing operations, and factory infrastructure are therefore central. But a modern foundry is also a design ecosystem company. Customers need PDKs, libraries, IP interfaces, reference flows, advanced packaging options, and technical support that allow designs to reach silicon successfully. This is why design enablement and customer engineering belong in the same landscape as process technology. The foundry career space is an excellent example of hardware manufacturing and design infrastructure converging around one customer outcome. Published foundry roles reveal two complementary forms of engineering ownership. One group develops and operates the physical technology devices, processes, equipment, control, yield, manufacturing, and packaging. Another group makes that technology usable by design customers through PDKs, IP, design flows, application support, and qualification. Neither side is secondary. A leading process node has limited value if customers cannot design into it successfully, while excellent enablement cannot compensate for unstable manufacturing. Students interested in foundries should therefore consider whether they are most energized by physical process development, high-volume manufacturing, computational infrastructure, or the technical interface between the foundry and its customers. Equipment and process control companies build the platforms that make advanced manufacturing possible. Their engineering spans process physics, plasma and vacuum systems, optics, electron beams, precision mechanics, thermal systems, sensors, control, software, algorithms, and applications. The work can range from fundamental R&D to customer site engineering, so it is important not to reduce this company type to either machine building or field service. The strongest opportunities often occur where disciplines meet, for example, when chamber design affects process uniformity or when sensing and algorithms enable tighter process control. This breadth makes equipment companies particularly relevant to mechanical, electrical, physics, materials, software, and control-oriented students. Published roles in equipment and process control companies repeatedly show multidisciplinary engineering. Process engineers develop or optimize the semiconductor process enabled by the tool. Mechanical and electrical engineers create subsystems. Systems engineers integrate them. Software and algorithm engineers control equipment and interpret sensor data. Applications and customer engineers connect tool capability to production requirements. The career question is therefore not simply whether you want to work on equipment. Ask which layer of the equipment problem interests you: the process, the physical subsystem, system integration, control software, data intelligence, or customer application. Each layer can lead to a technically deep career. EDA and IP companies turn semiconductor design complexity into computational infrastructure. Their work includes simulation, verification, synthesis, physical implementation, timing, extraction, manufacturing-oriented computation, IP, and increasingly AI-assisted design. The defining characteristic of core EDA R&D is that engineers create algorithms and software engines that other engineers use to design chips. At the same time, EDA companies also need product, applications, and customer engineers who deploy those tools in real design flows. This distinction is important. Creating a solver and applying a solver are different missions, even when both require deep technical knowledge. Strong candidates understand the underlying design problem, not only the interface of a particular tool. Published EDA roles often combine computer science with substantial semiconductor domain knowledge. Algorithm developers may need optimization, graph methods, numerical analysis, parallel computing, or machine learning, but the algorithms must still respect timing, geometry, electrical behavior, manufacturing rules, or verification semantics. IP roles add another dimension by delivering reusable design blocks and interfaces. Applications engineers connect these technologies to customer flows and often need hands-on experience with the tools. For students from computer science, this is an important message. Semiconductor careers can be software-intensive without being generic software jobs. Domain understanding is what turns computational skill into EDA engineering. OSAT companies specialize in outsourced semiconductor assembly and test, but advanced packaging has expanded the technical depth of that role considerably. Modern OSAT work can include package architecture, process development, bonding, substrates, thermal and mechanical analysis, test engineering, yield, reliability, quality, manufacturing, automation, and customer qualification. Chiplets and high-bandwidth memory make these capabilities increasingly important to system performance. Students should therefore avoid thinking of back-end manufacturing as merely the final step after the real engineering is finished. In advanced products, package and test decisions can determine bandwidth, thermals, cost, yield, and field reliability. Published OSAT roles reinforce the distinction among package architecture, package process, multiphysics engineering, test yield, reliability, quality, and manufacturing. These functions collaborate closely, but they solve different problems. A package designer defines structures and interconnects a process. Engineer establishes assembly windows. A test engineer develops screening methods. A reliability engineer evaluates lifetime. And a quality engineer coordinates corrective action and customer closure. The breadth of these roles creates opportunities for electrical, mechanical, materials, manufacturing, and data-oriented engineers. For career planning, the most useful question is which part of the package-to-product transition you want to own. Part 5 turns the industry map into a personal navigation tool. The following slides connect common academic backgrounds with missions where their existing knowledge can provide a strong starting point. These are not restrictions, and they are not predictions of who will succeed. Semiconductor engineering is too interdisciplinary for that. Instead, each map asks two constructive questions. Where does this major already provide useful foundations, and what bridge knowledge would make additional missions accessible? The final slides then focus on evidence how to show engineering capability through projects, analysis, implementation, measurement, and documentation, rather than relying only on course titles or tool familiarity. Major to career navigation works best when you separate foundation from destination. Your major shapes the problems you have already practiced solving, the mathematics and science you are comfortable using, and the kinds of evidence you can build quickly. It does not determine a permanent boundary. Published semiconductor roles frequently accept several related disciplines because the work itself crosses traditional departments. Use the next slides to identify natural starting points, then look for bridges into adjacent missions. A good bridge is specific one course, one project, one tool chain, or one domain concept that closes a recognizable gap between your current preparation and the engineering responsibility you want to pursue. Electrical and electronic engineering provides one of the broadest starting points because circuits, digital logic, signals, electromagnetics, control, and embedded systems appear throughout the semiconductor lifecycle. Natural entry points include architecture, RTL, analog and mixed signal design, physical implementation, verification, DFT, test, package electrical design, firmware, and equipment control. The breadth can also make career choice difficult, so depth matters. Rather than collecting many unrelated tools, choose a mission and build evidence around its core problem. For example, an RTL project becomes stronger when it includes verification and synthesis evidence. A package project becomes stronger when it quantifies signal or power integrity rather than remaining conceptual. Computer science and software backgrounds are increasingly important in semiconductors because both design and manufacturing have become deeply computational. Natural paths include EDA algorithms, system and chip software, firmware, factory software, equipment software, semiconductor data and AI, and some verification or architecture roles. The bridge is domain knowledge. A strong software engineer becomes much more valuable in this industry when the code is connected to timing, hardware interfaces, manufacturing data, design rules, or physical constraints. Portfolio work should therefore avoid generic applications when possible. Show that your software can reason about a semiconductor problem and that you understand how correctness and performance are validated in that domain. Mechanical engineering connects naturally to semiconductor equipment, precision motion, thermal systems, vacuum hardware, factory infrastructure, package thermomechanics, warpage, stress, and reliability. Advanced packaging has made this connection even stronger because mechanical behavior now interacts directly with electrical performance and assembly yield. The useful bridge is semiconductor-specific context material stacks, cleanroom constraints, process environments, package structures, and the scale at which deformation or vibration becomes critical. A compelling project might model thermal resistance, package warpage, precision positioning, or equipment dynamics and then connect the result to an engineering requirement. The goal is to show how mechanical reasoning influences semiconductor performance or manufacturability. Materials and metallurgy backgrounds are central wherever interfaces, films, interconnects, substrates, diffusion, stress, adhesion, and microstructure determine performance. Natural missions include materials engineering, unit process development, process integration, device engineering, advanced packaging, reliability, and failure analysis. The bridge into semiconductor work is often the relationship between material properties and electrical or manufacturing consequences. A materials study becomes more compelling when it explains why a phase, interface, or stress state changes leakage, resistance, adhesion, warpage, or lifetime. Students with this background should view semiconductor manufacturing as a rich materials system in which nanoscale films and package-scale structures are both technologically important. Chemistry and chemical engineering contribute directly to deposition, etch, cleaning, CMP, photoresist, contamination control, surface reactions, gas delivery, and many other manufacturing processes. Natural career paths therefore include unit process development, process integration, materials, equipment process applications, and some areas of factory infrastructure and process control. The bridge is often semiconductor device context and measurement, understanding how chemical conditions translate into profile, selectivity, film quality, defectivity, and ultimately electrical behavior. A strong project should connect reaction or transport reasoning to a measurable process outcome. That connection demonstrates that chemical expertise can be applied within the constraints of semiconductor manufacturing. Physics provides a strong foundation for device engineering, metrology, inspection, lithography, equipment R&D, reliability, and several computational roles. Semiconductor work draws on solid-state physics, optics, electromagnetics, electron beam interactions, transport, statistical behavior, and measurement science. The bridge depends on the mission. Device roles may require stronger fabrication and TCAD knowledge. Metrology may require instrumentation and uncertainty analysis. Computational lithography may require numerical methods and optimization. Physics students should not assume that an advanced degree is the only route into the industry, but they should examine current role requirements carefully and build evidence that connects physical theory to an engineering measurement, model, or design decision. Industrial engineering, mathematics, statistics, and data-oriented backgrounds are especially relevant to yield, manufacturing operations, factory software, process control, quality, and semiconductor data and AI. These missions depend on optimization, probability, experiment design, queuing, statistical inference, anomaly detection, and decision-making under variability. The essential bridge is physical context. A mathematically elegant model is useful only if its variables correspond to meaningful process, equipment, product, or factory behavior. Strong projects should therefore combine analytical rigor with domain interpretation. For example, explaining why a wafer map pattern suggests a particular mechanism or how a dispatching policy changes cycle time and bottleneck behavior. Strong student evidence answers an engineering question in a way another engineer can inspect. A screenshot showing that a tool ran is weak evidence because it reveals little about reasoning, correctness, or reproducibility. Stronger evidence includes a defined requirement, a design or hypothesis, measurable results, comparison against a reference, and an explanation of limitations. Excellent evidence goes further by exposing trade-offs, failures, and corrective reasoning. This principle applies across missions. RTL can be verified against a golden model, process data can be analyzed statistically, a thermal model can be correlated with measurement, and software can be benchmarked against a clear requirement. Evidence turns learning into credibility. Career evidence does not need to imitate an industrial project in scale. It needs to demonstrate the same reasoning pattern. A verification candidate can show a coverage-driven environment. A process candidate can show a designed experiment and process window. A packaging candidate can show an electrical thermal trade-off. A yield candidate can diagnose a synthetic or public dataset. A software candidate can integrate hardware and measure end-to-end behavior. A data candidate can connect model output to an engineering mechanism. The most persuasive projects are usually narrow enough to finish well. One carefully verified project can communicate more capability than several broad demonstrations that provide no evidence of correctness. Choosing a career direction is easier when you combine three perspectives: the engineering problems you enjoy, the capabilities you already possess, and the evidence you are willing to build. Interest alone is not enough, but neither is choosing only by current hiring volume. Technology trends change, and job titles change even faster. A durable choice is a mission whose underlying problems motivate you to develop deeper skill. Use current company postings to test the market, but use the mission framework to understand what those postings are really asking for. Your first choice does not need to be permanent. It needs to be specific enough to guide the next meaningful project. Once you have chosen a direction, build evidence deliberately. Start with one mission and identify the smallest project that can demonstrate its core engineering responsibility. Define a measurable target before you begin. Preserve intermediate results, including failures, because they show how you diagnosed the problem. Compare your result with a reference or baseline whenever possible. Document the boundary of what you proved and what remains uncertain. This discipline is valuable well beyond recruiting. It is the same habit that supports design reviews, technical reports, experiments, and engineering decisions. A portfolio built this way tells a reviewer not only what you studied, but how you think. The methodology behind this landscape is intentionally transparent. Public company career and technical materials provide the factual basis for role responsibilities and requirements. The 7 worlds, 35 missions, cross-company grouping, and major-to-career navigation are an educational synthesis of that material. They should therefore be used as a structured guide rather than as an official classification issued by the companies. Technology and hiring priorities also change, so current postings should always be checked when making a real career decision. The purpose of the framework is to make that research more intelligent. It gives you stable engineering questions with which to interpret changing titles and organizational structures. You do not need to know your entire career path before you begin. Semiconductor engineering is broad enough that many strong careers emerge through exploration. A design student discovers verification. A software student discovers EDA. A mechanical student discovers advanced packaging. Or a physics student discovers metrology. What matters is continuing to turn curiosity into evidence. Choose one engineering problem, learn enough to work on it seriously, build something that can be inspected, and reflect on what the result taught you. As technology evolves through AI, HBM, chiplets, new devices, intelligent manufacturing, and new software systems, there will continue to be meaningful challenges for capable engineers to solve.